Hello everyone, welcome back. In this video, you're going to learn how to apply Lasso regression using Python's Scikit-Learn library. As usual, I prepared a notebook for this video, and I will share a link to this notebook in the video description. I will also share the data file that I use in this video, so you don't need to worry about having access to the notebook or the data file, okay? Now, before jumping into the notebook, I think it is important to be clear about kind of the goal that we are pursuing when we apply Lasso regression. And that's why I prepared these 4 slides. Lasso is one of the methods that you can apply to address this question. How to select a good multiple linear regression equation. Because when we're trying to select a good multiple linear regression equation, we face this quandary. Should we include all the available predictors in the equation or only a subset of them? Okay, well, as you will see, Lasso targets that issue. Lasso means a least absolute shrinkage and selection operator. And when we apply Lasso, we are able to get this, an equation that excludes the irrelevant predictor. So the subset that we get with Lasso uh, supposedly only have the good predictors. So we exclude the useless predictors. And Lasso assigns a coefficient to each predictors whose magnitude, so the magnitude of the coefficient, reflects the predictor's importance. Okay, so not only we exclude from the equations irrelevant predictors, but in the equation we can see which one are the most important predictors depending on their coefficients. So that's really, really great. Now, how does Lasso work? Well, first, let's remember how a regular regression works. So regular regression in a more technical term is, ordinary least square regression. So this is kind of, regular regression analysis. So when you apply regular regression, the objective function, so the function that you're trying to minimize is this one, RSS, so residual sum of squares, also known as the sum of a square of error. What is residual sum of a square? So it's the sum across all the observations of the square difference between what? The difference between the actual values of the target variable, y, and the predicted values of the target variable. The predicted values of the target variable will be y hat. And what's the difference between the expression on the left and the expression on the right? Well, the difference is that on the right, I have replaced y hat, which is the predicted value of the target, by the equation that gives us y hat, okay? And that equation is just simply beta 0, which is the y-intercept, and then, as you can see here, the sum across all p predictors of the coefficient times its corresponding predictor. So each coefficient times its corresponding predictor, okay? So that's the objective function that we are trying to minimize when we apply ordinary least square regression, standard regression. What function do we minimize when we apply Lasso? Well, the objective function in Lasso is RSS again, so the same residual sum of a square, plus this term, okay? Now, what is this term? This is lambda, which is the regularization parameter, times the sum of the absolute value of the predictor's coefficient, so the coefficient for each predictor, okay? And, by adding this term, okay, by adding this term to RSS, Lasso will shrink towards 0 the coefficients of irrelevant predictors. That's why Lasso is it's one of the shrinkage methods. So Lasso, ridge regression, they are called shrinkage methods because they shrink towards 0 the coefficients for the least important predictors. Some predictors might even be assigned a coefficient or of exactly 0, and in that case, that means that Lasso is excluding that predictor completely from the equation. Okay. One thing to keep in mind here is that the larger the lambda, the larger the number of predictors that will get their coefficient shrunk towards 0. Okay, so a large lambda will kind of force Lasso to to shrink towards zero many coefficients. Okay. So in that case, so when we use a large lambda, so only the very important coefficients get coefficients different from zero. Okay. And guys, actually, when you apply Lasso, the decision that you need to make is what lambda am I gonna use? Okay, and that's what I'm gonna show you how to do in Python. So I'm gonna show you a procedure that you can follow to select a good lambda. So because in principle you don't know, like should I use a small lambda or a large lambda? All right, so let's go to Python to find that out. Okay. All right, so I'm going to use Python using Google Colab. So I prepare this Python notebook using Colab. Okay. Let's start by importing all of the functions that we're going to use in this video. Okay. So let me go ahead and execute that code cell. Done. And now the data, in terms of the data, what data we're going to use? We're going to use the auto data set, very kind of famous data set in the regression and machine learning community. So it's a data set with 392 different car types and models. And the goal with this data set is to predict a car's miles per gallon. So miles per gallon would be our target. Okay. Now, how do we access that data set? So I have that data set stored locally here. Okay. And in my downloads folder. And what I'm going to do is I'm gonna upload that to Colab. And to do that, this is what you should do, guys. So you should see this tab right here that says files. So you're gonna open that. And then now we're going to, let me remove it. So let me remove it to start over. So what you're going to do is you open the Files tab, okay? And then you grab just the files from your downloads folder or from whatever folder, and then you're gonna drag it and drop it right there in the Files tab. Drop it. You're gonna get that warning. Make sure that your files are safe because once you close Colab, the files disappear from the Colab session. That's fine. Okay, you click OK. And then this is what you do. Once you have the file here, which is a CSV file, you're going to copy the path to that file. That's very straightforward. You go to these three dots, copy path, and then now we can close this, okay? And close the Files tab. And then you're going to store, guys, that path in a variable. I created a variable path auto data to store that path. So inside quotes, you're going to paste that path, okay, the one that you copied, and then that's it. So that variable contains the path to that file. So we're gonna execute that code cell, and then you're going to use from the pandas library, you're going to use the read underscore CSV function to read that CSV file into a data frame. And I used I chose the name auto df for that data frame. Okay, so let's go ahead and execute that. Now let's take a look at our data frame, okay, using the info function. And as I said, we have data about 392 cars. For each car, we have data about its miles per gallon, the number of cylinders, displacement, and so on and so forth, okay? All right, so let's go now. So before we can apply Lasso, we need to do a couple of pre-processing steps. This data set is pretty clean, so we don't need to do a lot, but at least we need to do two things. And they are, we need to remove an unnecessary column. So the name column, which is just, like the name of the car, like, Toyota Corolla or Honda Civic or whatever, we don't need that column in a regression equation. We cannot use that column in a regression equation, so we're going to remove it from the data set. Okay, that's what I'm doing here by using the drop function. I want to remove the name column, and in place true means that, that I want that change to be permanent. Okay, and sure enough, execute that code cell. And now when you take a look at the auto data frame again, name is not there anymore. Okay, the second pre-processing step is regarding the categorical column that we have in the auto data set. Like all of the columns, as you can see, the data type is integer, float. Okay, so they're all numeric, But the last one is origin, and it's object data type. Object data type means it's categorical, it's qualitative, okay? Origin means the origin of the car, okay? Let's explore the origin column. And for that, I'm going to use value count. So whenever you are exploring a categorical column, value count is a good option, okay? And here we can see that we have three origins, American, Japanese, or European, and then the count for each origin. And remember that when you are applying regression, you cannot have categorical or qualitative columns. So all of your columns, all of your predictors or features must be numeric. So we need to convert that feature from categorical into numeric. And to do that, we're going to apply dummy coding. Okay, we're going to go ahead and apply dummy coding. And that's what I'm doing in this code cell. So from the pandas library, I'm using the get dummies function. And what I'm saying is from the auto data frame, I want to convert to dummy the origin column, okay? The origin column. Now, what does this parameter means? Drop first equals true. Well, remember that one requirement when you apply dummy coding is to drop one of the dummies, okay? So let's go ahead and execute that code cell to see the results. So there you have it. So all the columns, but now we don't have the original origin. We have two dummies, one dummy for the European cars and one dummy for the Japanese cars. So origin European will be true if the car is European, origin Japanese will be true if the car is Japanese. So as you can see, the dummy representing American cars was dropped. So remember that the dummy that gets dropped represents the reference level. What does that mean? So that means that origin European represents what happens when you compare European cars to American cars, because American cars are the reference. So the dummy that gets dropped is the reference, okay? And the dummy for Japanese means what happens when you compare Japanese cars to the reference level, to Americans, okay? So that's something to keep in mind. Okay. All right. So this sounds good. So what I want to do now is I want to store that data frame in a new data frame. Okay. And that's what I do in the next code cell. I repeat that same code again, but I stored that in a new data frame that I called AutoDF dummies. Okay. And sure enough, when you take a look at that data frame, now we have all the quantitative columns that we had initially and these two new the dummy columns and the data type for the dummy columns is Boolean, but that's okay because internally Python will treat the true values as 1 and the false values as 0. So Boolean it's okay. All right. So we're good. We're good. Now we can go ahead and apply Lasso. But before applying Lasso, I need to remind you something. How do you actually train a machine learning model? Remember that our goal is to find out what lambda to use. What is a good lambda to use? Like a small value, medium value, large value, okay? So how do we navigate that training process? For that, I'm gonna show you a chart from the Scikit-Learn documentation that represents that process, the process of training a machine learning model very, very well, okay? So let me open that link. Yes, let's go to a link. That's again, that's just a chart from the Scikit-Learn documentation representing that process. So when you're trying to train a model to find out among all the possible options, the best one, this is what you should do. You should get your data set and split it into training and testing. We're gonna do that. And with the training data, you should apply cross-validation. What for? What should you apply cross-validation for? To select among all the parameters, okay? And you can try a bunch of parameters to select among all the parameters what is the best parameter. So with the training data, we're gonna apply cross-validation to select among all the parameters what is the best one, okay? Then what we're going to do is we're gonna use the best parameters to train the model with the training data, okay? And we're going to obtain what they call a retrained model. I prefer to call it the final model. So the final model is the model trained on the training data using the best parameters. And what do we do with that retrained model or final model? We predict the test data and we come up with the final evaluation. We're going to follow those steps, all right? Okay, let us go. Let's go ahead and start by splitting the data. First step, right? Okay, let's split the data. And to split the data, I always like to first, create one variable storing all the predictors. So X auto includes all the predictors. X represents the predictors, okay? And I also like to create a variable to store only the target, only the outcome, okay? Miles per gallon. And once I do that, I do the splits. To do the split, I'm going to use this function, train test split. And the output from that function will be four different objects, as you can see. So the output from that function will be these four objects. I'm trying to highlight them. Sorry about that. These four objects. There you go. Those four objects. Okay. X train, X test, Y train, Y test. Okay. But now a little bit about the arguments that I use for that function. Well, here the first argument is just the variable with all the predictors, then the variable with the target, then what is the test size. So I'm going to do an 80-20 split. So I want 80% of the data for training and 20 for the test. So test size 20%. Okay. And what is this random state equals 1? What I'm doing there, I am setting the random seed equal to 1. What does that do? That controls the randomness of the split. Okay, that controls the randomness of the split. Okay, because I want to make sure that when you use this notebook, you get the same split that I'm going to get right now. Okay. Okay, so let's go ahead and execute that code cell, and let's take a look at all of these objects. Okay, xtrain. What is xtrain? Well, it's a data frame with only predictors. So I don't see miles per gallon there. It's only the predictors. And we don't have 392 rows. We have 313. 313 is 80% of 392. What is xtest? Xtest will be a data frame with only the predictors, okay? And for X-test, we only have 79 rows, 79 observations because it's 20% of 392. White train will be a series, a Panda series with just, the values of the target for the training data, and white test will be the values of the target miles per gallon for the test data, okay? All right, perfect. So we did the training, I'm sorry, we did the split. Now we are ready to apply Lasso regression. Now, to apply Lasso regression, we should standardize the predictors. Why? When you are using a technique that applies regularization, like this, okay? When your objective function applies this kind of regularization with a regularization parameter, you must standardize the predictors. Standardize the predictor means, like, for each predictor, you're going to compute its mean and standard deviation, and then from each value, you're going to subtract the mean and divide by the standard deviation, okay? So that's a requirement whenever you're using a technique that applies regularization. Perfect. So we need to standardize the predictors, but here's the question. How should we standardize the predictors? There is a correct way and an incorrect way. The correct way to standardize is this one, two-step process. We need to obtain the mean and the standard deviation for each predictor from the training data. And then we need to use these means and standard deviation, so the mean and the standard deviation for each predictor, to standardize both the training data and the test data. So from the training data, we get the mean and standard deviation from each predictor, and we use those means and standard deviations to standardize both the training data and the test data, okay? We have many ways of accomplishing this, okay? Standardizing the predictors in the right way, but I guess the simplest way recommended by Scikit-Learn is to use a pipeline object, okay? With a pipeline object, Scikit-Learn internally will take care of that standardization following the right way, okay? Now, to create a pipeline object, one way is to use the make pipeline function. And in that pipeline, notice that I am including two things. So a standard scaler is the function that allows us to standardize. And I'm also including the application of Lasso. That's a nice thing for pipelines. So with a pipeline, you can have like kind of a pre-processing steps like standardization, and also you can include the technique that you want to apply. So if we were applying here, I don't know, regular regression instead of Lasso, we can apply linear regression or rich regression. So whatever technique you're applying, logistic regression, okay? So in the pipeline, we're going to include two steps: a standardization, and then the technique that we are applying, which is Lasso, okay? Cool. So let me go ahead and execute that pipeline. I stored the pipeline in this object, pipeline Lasso. Now, ready to apply Lasso, but then we need to select a good lambda, okay? What I'm going to do is I'm going to try a bunch of lambdas. So I'm going to try really small lambdas, which means weak regularization, then intermediate lambda, and then larger lambdas, which means strong regularization, okay? So I'm going to try a bunch of values, and then let cross-validation decide what is the best one, all right? And the thing that you need to notice is that, unfortunately, in Scikit-Learn, they don't call it lambda, they call it alpha. So the parameter is not called lambda in Scikit-Learn, it's called alpha, okay? That's okay. And as I said, I'm gonna try a bunch of values. 0.001, that's a very weak regularization. 0.01 also is a weak regularization. 1 means intermediate level of regularization. And then, for example, 50 and 100 means very strong regularization. So again, in principle, I don't know what is a good value of lambda or alpha. So I'm gonna let cross-validation decide, okay? To apply cross-validation, I'm going to apply the grid search cross-validation function, okay? With grid search, what we're going to do is we're going to evaluate each of these values of alpha using cross-validation. So we're going to apply cross-validation for alpha 0.001, then cross-validation for alpha 0.01, and so on and so forth. And then we're going to see which one of those alpha leads to the best cross-validation result, okay? To apply grid search cross-validation, what I'm going to do first is I'm going to create a variable that defines how the cross-validation will take place. So before applying grid search itself, I kind of define how the cross-validation will take place. And for that, I'm going to use the k-fold function. K-fold function, using the k-fold function, I can specify the following. I can say, you know what, I want to use 10 splits or 10 folds. So I'm gonna apply a 10 folds cross-validation. Yes, I want to shuffle the data. I want to randomize the data before applying cross-validation. And random state 1 means that, again, I'm setting the seed to 1 to control the randomness. So I want to make sure that you and I get the same folds after applying cross-validation, okay? Just to make sure we can have reproducibility in my results, okay? All right, so let's go ahead and execute that. And once I define that, I can actually apply the grid search, okay? Grid search cross-validation function. I stored the grid search cross-validation set up in this function. I'm sorry, in this variable, Lasso grid search. Now let's try to understand the arguments for grid search cross-validation. The first one is the estimator. Like, what is the technique that you are applying? What is the model that you are applying? And notice that the estimator, the argument that I passed was pipeline Lasso. So what is pipeline Lasso? It's a pipeline with two steps, standardization and Lasso. So I'm telling Scikit-Learn, hey, I want to apply Lasso, but before applying Lasso, I want to standardize the predictors the right way, okay? Param grid is just what is the object that stores all the parameters that you want to try, okay? And that would be hyperparams grid search, okay? Next is scoring. Scoring is negative mean square error. Okay, what is that scoring? Scoring defines how you want the model obtained from the training faults evaluated on the test fault. So what we're saying here is that we want to compute the negative mean square error on the test fault for the model obtained from the training faults, okay? And ideally, we don't want the negative mean square error, we want the mean square error, but Scikit-Learn does not give us that option for reasons that I'm not going to discuss. There is a reason for that. So there is a reason for why we don't have mean square error in Scikit-Learn, but it's beyond the scope of this video. And but that's okay, you know, because we can easily transform negative mean square error into mean square error by multiply by -1, okay? And that's what we're gonna do. And CV setup is just the CV setup that we define here, okay? Okay, so that's the grid search setup, if you will, okay? So, and again, I store that setup or that definition in this variable, Lasso grid search, okay? Now, in this next code cell, I'm actually feeding or running the grid search, okay? So when you invoke the feed method using the training data on the grid search, you're actually running the grid search, okay? And remember, we need to run the grid search on the training data. You need to find the best parameters using cross-validation on the training data, okay? So we apply cross-validation to select the best parameters using the training data. So that's why here, the arguments I'm passing to this function are xtrain and ytrain, okay? The predictor for the training data and the outcome or target for the training data, okay? All right, so let's go ahead and run that. It's gonna take a few seconds only and done, it's done. So the grid search is done. Now we can inquire that grid search. Hey, what was the best alpha? What was the alpha with the best cross-validation result, okay? And to do that, we can use the best params attribute. So from that the grid search that we define, we can get the best params, and we need to specify what parameter do we want, okay? And the parameter that we want is alpha, okay? And the best alpha was 0.05, okay? Now, if you're interested in knowing, okay, what was the negative mean square error for that alpha? So what was the cross-validation score for that best alpha? We can do that easily. So we can retrieve the best score. The best score would be the best negative mean square value for that alpha, for the best alpha. So the best score is the negative mean square error for the best alpha. And what I'm doing here is I am changing that from negative mean square to mean square by multiplying by -1. Okay, notice that -1 right there. Okay. And here's the result. So the cross-validation MSC with the best alpha was 17.53. Cool. Now, this is fine. You know what? At this point, we can go ahead and jump to the next step. So we can use the best parameter, alpha 0.05, and train a lasso regression using the training data. Okay, so we can just go ahead and jump to this step now to obtain the retrained model with the best parameter, alpha 0.05. Okay, I don't want to do that yet because sometimes this result is a little bit, how should I say, misleading? Not misleading, but um, incomplete is better, incomplete. So sometimes like this result is incomplete in the sense that it looks like the best alpha is 0.05 and the other alphas like maybe are not that good. That's not true. Sometimes many alphas are equally good. There is one that is slightly better, but sometimes when you explore further, you notice that many alphas are equally good. That's what I want to do. So that's what I want to retrieve. And this is kind of optional, okay? You don't need to do this, but I like to do it. I like to retrieve the full cross-validation results for each alpha to get a better idea of what the best and worst alpha are, okay? To do that, from the grid search, I'm gonna retrieve the CV results attribute. I'm gonna store that in a data frame called CV results data frame, okay? And that data frame has 8 rows. Why 8 rows? Because we have um, one row for each of the alpha. We have 8 values of alpha, okay? And for each alpha, we have all of this information, okay? Mean feed time, standard deviation feed time, so how long it took to feed the cross-validation for each alpha. And but what I really care about are only 2 columns. I want to get, for each alpha, I want to get the alpha itself, so the alpha listed, and I also want to get the mean test score. The mean test score is the mean cross-validation score for that alpha, okay? So in short, from that data frame, I'm gonna get a reduced data frame with only 2 columns, okay? Let's do that, okay? So that's what I'm doing here, alpha and the mean test score. And that's the data frame that I want to focus on, okay? Now, I want to modify that data frame a little bit because, for example, I don't like that name. I want to change that name the name of that column from that to simply alpha. And I also don't like that name. That name is correct, but might be misleading, confusing. Okay, so instead of calling this mean test score, I want to call it mean cross validation MSE. That's a more accurate name. Okay, mean cross validation MSE, and I also want to turn the negative values into positive ones. So because right now we have the um, negative mean square error, I want to get the positive mean square error. Okay, I accomplished all of that in this code cell, and this is our new data frame. Cool. All right, and just take a look at that, guys. It's true that the best, like the lowest mean cross validation MSC happens with 0.05, okay? 17.52. But guys, like other alphas give us very similar cross validation MSCs. 0.10 give us a cross validation MSC of 17.53, almost exactly the same as this. 0.01 give us a cross-validation MSC of 17.60. So very close to this, 17.52, 1760, which is very close. Okay, so again, to get a better idea of like not only the best single alpha, but the best alphas, I like to do this summary. Okay, and but it's, as I say, it's always better to represent this graphically, than to just observe this in a table. So that's why I'm going to represent this graphically. So I'm just gonna do kind of a plot showing on the x-axis the different values of alpha, and on the y-axis the mean cross-validation MSC for each alpha. We have a problem here because like the values of alpha cover a very large range from 100 to 0.01. And as a matter of fact, I think we have like 3 or 4 values in between 0 and 1. So that's why the values in between 0 and 1 are all grouped together here. So you cannot really see what's going on. So in that case, it's the recommendation is to use a logarithmic scale, okay? So what I'm going to do is to that code, I'm going to add one line only, this one. X scale log, because I want to use a log scale because of what I said, because the values of alpha cover a very large range. And you'll see that this is much better to interpret, okay? Now we can see, all the values of alpha and what is really going on. What's happening here, guys? As I said earlier, yes, the lowest cross-validation MSC happens here at that point. That point is alpha 0.05. But as a matter of fact, you know what? Like all of these alphas from 0.001 to 0.1, they're just very similar. We kind of see the first increase, the first obvious increase in cross-validation MSC happens when we go from 10 to the negative 1, 0.1, to 10 to the 0, 1. So the first increase in cross-validation MSC happens when we go from alpha 0.1 to alpha 1. Okay, but before that, so for any alpha less than or equal to 0.1, guys, the performance is very similar, okay? And that's actually what I said here. Although the lowest cross-validation MSC is achieved at alpha 0.05, the results show that any alpha less than or equal to 0.1 performs very well, okay? So this gives us a more complete picture of what is going on instead of that, kind of very limiting result. Oh, the best alpha is 0.05. Well, not really. There are many alphas that are equally good, okay? And I also want to point out that since the best alpha seems to be less than or equal to 0.1, what does that mean? That suggests only a low level of regularization. So it looks like for this data set, and this is very important, for this data set, Lasso is telling us that you should use a low level of regularization, okay? Because alpha 0.1 or less, it's a low level of regularization, okay? Okay, so well, now we know, that supposedly the best alpha is 0.05, and we can use that to retrain our model to then use that retrain model to predict the test data. But before doing that, I want to do one more thing. I want to take a look at the coefficients, okay? I want to take a look at the coefficients because remember what I said here. Lasso should supposedly exclude irrelevant predictors, and also it assigns coefficients to each predictor whose magnitude reflects the predictor's importance, right? So let's do that quickly before predicting the test data. That's feature importance. And feature importance, what I'm going to do is I'm gonna just retrieve the coefficients, guys. So I'm gonna retrieve the coefficients from the grid search. So from the grid search, I'm gonna retrieve the coefficients, and I'm gonna store the coefficients in a data frame where I'm gonna store actually the coefficients and also the absolute values of the coefficients, because the thing is, the larger the absolute value of the coefficient, the more important the coefficient is. Okay, so let's create that data frame. And as you can see, this coef best lasso data frame will give us each coefficient, each predictor, its coefficient, and the absolute value of the coefficient, okay? To get a good idea of what the most important predictors are, let's sort this from highest to lowest, okay? From largest to lowest regarding absolute value. Okay, that's what I'm doing here. And now this allows us to identify the most important predictors and the least important predictors. As we can see, the predictor with the predictors whose coefficient has the largest absolute value is weight. Okay, weight has the largest coefficient in absolute value. So that means that weight is the most important predictor for predicting miles per gallon. Okay, so weight is the most important predictor for predicting miles per gallon. The relationship between weight and when you look at the raw coefficient, you can see it's negative. So the relationship between weight and miles per gallon is negative, which makes sense. Like heavier cars, then less miles per gallon. Okay. All right. So the second most important predictor, according to the absolute value of the coefficient, is horsepower, and it's also negative. So again, makes sense. More horsepower, less or fewer miles per gallon. Okay. And so on and so forth. Okay. And So, and one important thing here is, like here you can see, like for example, acceleration has a coefficient very close to 0.04. So that means acceleration is a kind of not very important predictor according to Lasso. And notice that displacement gets a coefficient of 0. What does that mean? What I told you earlier, that Lasso excludes displacement completely from the regression solution. Okay, so displacement is completely excluding from the regression solution. So according to Lasso, in your regression equation, you should only have weight, horsepower, or in Japanese or in European, cylinders and acceleration. Okay, not displacement at all. Okay, cool. Last step. Let's go ahead and obtain the retrain model. The retrain model is the model with the best parameter. In our case, the best parameter was alpha 0.05. And let's use that retrain model to predict the test data and obtain a final evaluation. That's what I'm doing here. Scikit-Learn gives us a very easy way of retrieving the best model. The best model is easily retrieved by using the best estimator attribute. Okay, so you invoke the best estimator attribute on the grid search, and then you're gonna get the model with the best alpha. Okay, in this case, the model with alpha 0.05, and we're gonna use that model to predict the test data. Okay, and we're gonna store the predictions in that variable. Why predict Lasso test? And then after that, I'm gonna compute the root mean square error on the test data. So that's why I like to call it the test root mean square error. And to compute that, we're going to use the actual values of the target on the test data and the predicted values of the target on the test data that we just computed here, okay? And the test root MSE is 4.42. So since our target is miles per gallon, 4.42 means 4.42 miles per gallon, okay? So that's kind of not exactly, but not exactly that, but kind of the average difference between the actual values of miles per gallon and the values of miles per gallon predicted by the equation. Okay, so it's kind of the average difference between real values and predicted values. Is that low enough? Is that error low enough? Are we happy with that error? Well, that's hard to say. Okay, it's hard to say. So by itself, like 4.42 miles per gallon, is that a good value for a prediction error? Not very easy to say because it depends on the context. It depends on the context. That's why what I like to do, and actually I like to do it because it's a kind of a standard recommendation in machine learning and statistics. You need to put that error into context. You need to put that error into context. There are dozens of ways of putting an error into context. The classical way is by computing the coefficient of variation. The coefficient of variation expresses the error, the RMSE, relative to a typical value of the target variable, in this case, the mean. So the coefficient of variation compares the error with, with the mean of the target variable, okay? Which again, the mean is a typical value. So you're doing a comparison of the error with the typical value of the target, in this case, the mean, okay? So that's the formula of the coefficient of variation, and that's what I'm going to do now. I'm gonna get the mean right here, and now I'm gonna compute the coefficient of variation. RMSE divided by the mean. And this is our coefficient of variation in percentage. In percentage, it's a percentage, okay? So it would be 18%. So what do we say? Is this 18% low enough to claim that the RMSE is good? Well, the overall recommendation or the overall rule, if you will, is if the coefficient of variation is less than 10%, that's a very good coefficient of variation. If the coefficient of variation is between 10 and 20, uh, then you should say that the coefficient of variation is, let's say, acceptable. It's decent, okay? So when the coefficient of variation is between 10% and 20%, then you can claim that the RMSE has a, it has an acceptable value, okay? So we can do better. We should aim for less than 10% for the coefficient of variation, but it's acceptable, okay? So in our case, so this Lasso regression is giving us a test error that is acceptable because the coefficient of variation is less than 20%, okay? All right, guys, that's all for this video. I hope you enjoy and learn a lot, and I will see you in another video. Bye, guys.